Okay. So we started yesterday talking about the last thing we started talking about was the boundary layer equations, right? So let me connect my pad. Yes. Okay. So we are talking about boundary layer equations. And as I told you, the main, just to repeat from yesterday, the main idea is, of course, we have the same physical principles and same governing equations, basically the momentum mass conservation equations. However, due to the fact that, as we discussed yesterday, the fact that the boundary layer thickness, let's say, the highest level that you can reach at the, I don't know, end of this geometry, this flat plate, compared to its characteristic length, like the chord, for example, so delta over C, generally is very small number. Okay, so delta is generally much smaller than the chord. So in this case, the governing equations, they do get simplified. And as we said yesterday, in order to see this effect, and by the way, you see that this delta over chord is a non-dimensional quantity. In order to make use of this fact, let's say, and this fact is justified over many different wind tunnel measurements and everything. The thing is, in nominal operational regime for an aircraft, when it's flying and at a certain condition, and if there's no flow separation or anything like that, this is indeed the case. Okay, so basically, in order to make use of this, we said we need to obtain the non-dimensional form of the equations first. Okay, non-dimensional form of the conservation equations, and for that purpose we introduced, for example, some non-dimensional parameters like u star, v star, p star. Yesterday we did that. And then for example, for the velocity values we used u infinity to non-dimensionalize. For pressure we use p infinity to non-dimensionalize, so on and so forth. And for x and y coordinates we used c, the actual characteristic length of the object. So x over c and y over c were the non-dimensional quantities. So for example, for the x momentum conservation equation, when we non-dimensionalize each and every single term in the equation, and as we did yesterday, like the first term was, for example, it looks something like this for the dimensional equation, rho times u du dx, right? So basically what we do is we divide this by rho infinity. So I have to multiply with rho infinity, divide this by u infinity. I have to multiply with u infinity, and then divide this by u infinity. So I have to multiply with u infinity square. So divide this by c. So I have to divide by c, okay? So this by c. And if I do that, is there a question?
Bekleme odasında olanlar varmış galiba hocam da.
Okay, şimdi aldım. Teşekkürler. So when we do that, we obtain for every single term in the x momentum equation, we obtain what we call the non-dimensional form of the x momentum equation. And how does it look like? And by the way, just to recap again, for example, for velocity, we said the star value is the non-dimensional quantity. It's equal to u over u infinity. So for other parameters, we did similar. So when we make use of this, for example, the non-dimensional form looks something like this: rho star times u star du star over dx. I'm not going to rewrite the dimensional form, which I did yesterday, but I'm going to write the non-dimensional form. And each time we non-dimensionalize, you see we start obtaining a collection of these quantities that we use for non-dimensionalization, right? So basically, after reorganizing, I will collect all these all these terms that we multiply to the right hand side of the equation. So let me first finish this. For rho v star du star over dy star, by the way, that should be x star, right? And now on the right hand side, normally we have a dp dx term, pressure gradient, but in front of it now we will have a collection of variables p infinity over rho infinity times v infinity square times dp star over dx star, and plus a collection of variables again, mu infinity, the viscosity, divided by rho infinity times u infinity times chord, okay, multiplied by d over dy star of the viscous term, so times mu star multiplied by dv star over dx star plus du star over dy star. So, I mean, mathematically, this non-dimensional equation, I mean, let me zoom out so we can see the whole thing. This non-dimensional equation actually looks very similar to the dimensional one, with only two major differences, okay? I mean, the dimensional form is exactly like that, except we do not have these variables in front of these terms. Okay, so this is one difference. Plus, these non-dimensional terms, since all these terms are non-dimensional, for example, the value for u star, right? U star changes from it has a numerical value that could change from 0 to 1, for example, or it could very well, of course, have a negative value, but its order of magnitude, we say that its order of magnitude will be around 1. Even if you are, let's say, even if your physical velocity is, let's say, 500 meters per second, which 500 is a number which is not the order of 1, which is actually a number order of 100. So even if you're moving at 500 meters per second, this u infinity will also be probably around 500, I mean, some within the same order of magnitude of this speed, so 550, 600. So this number, when you divide this number, I mean, this non-dimensional parameter, maybe I should say it like that, will always be a number that is in the order of magnitude of 1, okay? So that is the second, let's say, difference between the non-dimensional equation and the dimensional equation. The terms are generally in the order of 1, and we end up with having these extra multipliers in the equation. By the way, these extra multipliers, for example, this one is what we know as the Reynolds number, based on infinity, 1 over Reynolds number, actually. Because Reynolds number is defined by u times rho times, u times c divided by mu over rho, which is kinematic viscosity. So this is that. This is basically the multiplier here is 1 over Reynolds number. The multiplier on this side, it can be shown that this is simply equal to 1 over gamma times m infinity square. This is the Mach number. So if you remember, Mach number is indeed also a non-dimensional quantity. Gamma, the specific heat ratio we have seen in the first part of the semester, is indeed a non-dimensional quantity. And Reynolds number is also a non-dimensional quantity. So this entire equation is therefore a non-dimensional equation. So we will after obtaining this non-dimensional form and seeing that we have these extra multipliers and knowing the fact that these terms are generally in the order with they have an order of magnitude of 1, then the next step is to apply this observation, the fact that this delta over c is not is not the order of magnitude of 1. It's actually much smaller than that. So we will make use of that in a second. The first example we will use, instead of starting with this non-dimensional form of the momentum conservation equation, we will start with the non-dimensional form of the continuity equation, which is quite simple. So I did not derive it, but I guess you can do it yourselves with the same idea. The non-dimensional form of the continuity equation for a steady, incompressible flow is like this. Actually, it's for a steady flow only. Rho can be changed. It is within the parentheses. So d rho star, d u star, d rho star u star, d x star plus d dy star of rho star v star must be equal to 0. So this is the continuity, a non-dimensional continuity equation. So on this equation now, we will apply this, what we call in boundary layer theory, the order of magnitude analysis, okay? So order of magnitude analysis. And this order of magnitude analysis is a methodology, and it's very simple. It says that, okay, go look at each and every single term here. Take a look at this rho star or u star and x star, and try to determine try to guess their order of magnitude. Do they have an order of magnitude of 1 or smaller or larger? Okay, so that's what we mean by an order of magnitude analysis. So for example, u star, okay, u star varies between more or less 0 and 1. Okay, so across the boundary layer, that is, we are right now focusing ourselves to the boundary layer, not to any general fluid mechanics problem, to the boundary layer. So the variation of u, u is 0 on the wall, and you goes to u infinity or u edge, let's say. If it's a flat plate, they are the same thing, but u infinity near the edge of the boundary layer, so it changes more or less from 0 to 1. Okay, so we say that if it changes from 0 to 1, u star is it has an order of magnitude of 1. Okay, u star. Similarly, if you do the same thing for rho star within the boundary layer, it also rho star is rho over rho infinity, and so similar discussion, it will also have an order of magnitude of 1. So it changes from the numerical value of rho star will be a number that has an order of magnitude around 1 or 1. Okay.
Hocam,
Yes.
is it O in parenthesis 1, right? Not
Sorry,
0.
what?
O1 yazıyoruz değil mi hocam burada? Order fonksiyonu temsil etmesi için 0-1 değil. Tamamdır.
Order of magnitude. This is order of magnitude. That's how we show order of magnitude. So O, this is not 0, this is O. Parenthesis 1 means it does have an order of magnitude of 1. Yes?
Teşekkür hocam.
Across the boundary layer. So we have other parameters. We have x, for example, or x star actually. Yeah? And now x star changes from 0 to c, right? It is x. This is x over c. That's how we defined x star. So this is equal to 0 at the leading edge of the flat plate, and it's equal to c at the trailing edge of the flat plate. So x star changes from 0 to 1, and x changes from 0 to c. Therefore, this x star is also a parameter that has an order of magnitude of 1. Okay, what else? Let's see y star. Okay. Now, the thing is, y star is is related to the coordinate along y direction. But the y coordinate varies from 0, and we are discussing the variations within the boundary layer, and the y coordinate, basically the most important variations in the flow field occur within the boundary layer. So the y coordinate changes basically, or the most of the flow variations occur within a y range from 0 to delta across the boundary layer. Okay, this therefore is the changes happen from 0 to delta. This is 0, by the way. This is not ordered right now. From 0 to delta across the boundary layer. So in reality, this y star order of magnitude is approximately in the order of delta over c. Okay, so it's not this y star parameter. It does not have it's not at an order of magnitude of 1. It is an order of magnitude of delta over c. So, well, if we take a look now, what we got here. Let me rewrite the equation again. So our original mass conservation equation looks something like this. And the non-dimensional form, rho star v star. Now we discuss the order of magnitude of these terms. So what we got here is this one. For rho star, it is, let's say, order of 1. U star, it is order of 1. And X star is order of 1. So the first term basically is all has an order of magnitude of 1. The second term, rho star, has an order of 1. Y star has an order of delta over c, not 1. So this is actually smaller. And V star, what is V star? It's V over U infinity. So we are talking about the second velocity component. So the velocity component along Y direction, yes? So within the boundary layer. So anywhere within the boundary layer, if we have a V component, and when we non-dimensionalize it with U infinity, that's our V star. And indeed, this vertical velocity component also changes very little within the boundary layer. So in fact, this is also V star order of magnitude is also comparable to delta over C. Okay. So therefore, if you look at here, the first term is order of magnitude of 1, and these two terms actually have the same order of magnitude. So the second term is also in the order of magnitude of 1. So basically, the result of this analysis says that all the terms, the first term of this equation and the second term of this equation, they are in the same order of magnitude. So we cannot say that, for example, the second term is much smaller than the first one, so I will neglect the second term. We cannot say that. Or we cannot say vice versa. The first term is much, much smaller than the second term, so let's neglect the first term. We cannot do that. So, which means that this order of magnitude analysis that we applied for a thin boundary layer does not result in any kind of simplification for continuity equation. So we have to keep all these terms. We cannot neglect any of these terms and solve the equation when necessary. Okay, so but this is not the case when we deal with the momentum equation. And indeed, we will see in a second now that when we perform a similar order of magnitude analysis for example, the X momentum equation, indeed, some terms will cancel out and actually disappear. And disappear meaning some terms will be smaller than the other terms. And even more interesting than that, when we apply, and we will do that also, when we apply the order of magnitude analysis to the Y momentum equation, almost everything will disappear. Only one term will remain, and that term will have to be equal to 0. So the entire y momentum equation almost disappears after this application of the order of magnitude analysis, based on the fact that some terms are in the order of magnitude of delta over c, so quite small order compared to 1. We will see that. But let's take a look now. So the exercise that we did was for the continuity equation until this point. Now we will take a look at the terms of the momentum equation. Okay. For example, we will look at the terms one by one. So terms of the momentum equation. And first, maybe I should say x momentum equation. So the first term, let's write it down. It is equal to rho star times u star du star over the x star. Okay. Obviously, this will have an order of magnitude of 1 because each term it has an order of magnitude of 1, like we did before. The second term, rho star v star du star divided by dy star. Now, rho star order of magnitude of 1, u star order of magnitude of 1, v star order of magnitude of delta over c, and y star the same, so order of magnitude of delta over c. So these two, let's say, small terms cancel each other out. So indeed, this full term becomes order of magnitude of 1. What else we have in the equation? For example, we have the pressure gradient term, the p star over the x star in the x momentum equation. We have that. So p star is p over p infinity. So this is indeed order of magnitude of 1. This is order of magnitude of 1 x star. So this is also order of magnitude of 1. So until this point, we didn't lose anything. See, the order of magnitude analysis says don't ignore anything. Don't ignore any of these terms. Just keep them in the equation. But we have two more terms. Let's see what they are. We have the first term from the related to the viscous term, dy star of mu star dv star dx star. Okay. Now, basically, if you do this analysis with the second order derivative and everything, you will also see that this is also an order of magnitude of 1. Okay. But the last term, mu star times du star dy star, we see that this is at an order of magnitude of 1 over delta square over c square. Now that is interesting because delta over c is already a small number. And if you take the square of it, delta square over square, this one becomes a very small number. So when you get 1 over that very small number, the order of magnitude of this becomes a very high. So this basically becomes a very high number compared to this, for example. Okay, so that's interesting, and we need to now we need to use this in our modified equation, x momentum equation. So the non-dimensional form. Let me write this down. Therefore, the momentum, or let's say x momentum equation, will be in the order of, so the first term order of 1, we have a second term order of 1, we have this dp dx term, but that is multiplied with 1 over gamma and infinity square. dp dx itself is order of 1. We have 1 over Reynolds infinity multiplied by 2 terms. The first term is order of 1, but the second term is order of 1 over delta square over c square. Okay. This is a quite large number. Okay, in terms of order of magnitude, it is a very high order of magnitude, and it's much larger than 1. Compared to this is a small number. And what about the Reynolds number? What about the Reynolds number? So we have basically, if you using the Reynolds number definition, and this is indeed 1 over Reynolds number. So the order of magnitude of this coefficient itself is delta square over c square. Okay, so it is still not, it is actually a small number. But if you make this, so this is order of delta square over c square, order of 1 over order of delta square over c square. So this is a very large number multiplied with a actually a small number, and this is a small number multiplied with a small number. Okay, so basically, I mean, small number meaning this is a small number, this is a small number. When you multiply these two small numbers, but this is a very large number. When you multiply this one, a small number, it will basically become comparable to these terms, order of 1. So which means that in our equation, in fact, when I can basically neglect the first term here, because I'm multiplying an order of 1 term with a very small number. So this will become a very small number compared to the other terms in the equation. So I can basically neglect this term from the equation. So one level of simplification comes in here. So after dropping, or let's say ignoring smaller terms determined from this order of magnitude analysis, our x momentum equation now looks something like this. We keep this term because this is order of 1. We keep the second term. This is order of 1. We keep the pressure term, so minus 1 over gamma m infinity square dp star dx star. So we keep that, but only simplification comes in the last part. So we keep only the first term, 1 over Reynolds infinity, I'm sorry, the second term, d dy star multiplied by mu star du star dy star. And we drop the first term. Well, what happened here? We just got a, first of all, let's recap. The order of magnitude analysis did not change anything for the conservation of mass equation. The order of magnitude analysis did help a little bit in terms of simplifying the equations, because we were able to ignore one of the terms in the viscous term, so it doesn't show up in the equation anymore. Okay, so just as a side information, in parentheses, I would like to write here the corresponding dimensional form of this. Okay, so rho u du dx plus rho v du dy is equal to minus dp dx plus d dy of mu times du dy. Okay, so this is the corresponding dimensional form of this simplified, or maybe I should say a little bit simplified equation after order of magnitude analysis. Now, okay, but these two, yes, huh?
I would like to ask, how did we just write the order of magnitude as delta square over c square for 1 over Reynolds number?
It's based on the Reynolds number definition, yes. Let's see, it's up here somewhere. Here, this is the Reynolds number. Okay.
Okay.
And let's see. You are right. It's not actually that straightforward. You cannot see it from this equation, right?
Yes.
Okay, I will try to find a better way to explain it. Okay, I will check it because the thing is the order of 1 over Reynolds number is delta square over C square, not the order of Reynolds number itself, order of 1 over Reynolds number. Okay, order of 1 over Reynolds number, which means that, I mean, for example, let's say for typical, I don't know, aircraft operation, aircraft wing, let's say, typical, or helicopter blade or whatever, typical Reynolds numbers are like 2 million, 3 million, 4 million, things like that. So we are talking about a number, a numerical number, 1 over, for example, 4 million. Okay, so
Okay.
0.25 times 10 to the minus 6. So that is indeed a small number, yes? But in terms of boundary layer analysis, why is this delta square over C square, where is it getting generated? You are right. It's actually not very straightforward from this equation. I will check that. Okay, I will explain it next time.
Okay,
I will find a better explanation. And practically, I guess you could understand when you divide it with some millions of numbers, like some number that has the order of magnitude of 6, which is a typical Reynolds number, then yes, and indeed the fact is at those high Reynolds numbers, the boundary layer thickness is indeed small. And if you are, let's say, operating at small Reynolds numbers, this boundary layer thickness actually may not be small, and this approximation will not be valid anymore. But anyway, I will find out this discussion and explain to you later, okay?
Okay, sir.
So that was the X momentum, but we indeed have the Y momentum equation. The Y momentum equation, when we do, I'm sorry, order of magnitude analysis for the Y momentum equation, for example, let's take a look at one of the terms. I will not repeat everything for the Y momentum equation, but for example, the first term will be rho star U star dV star over the X star. Okay, so order of 1, order of 1, order of 1, but order of delta over C. So automatically this term will be actually order of delta over C, because you are multiplying, let's say, 1 with a very small number. Okay, order of 1 with a very small number. Similarly, I mean, if you keep doing this, in reality, all the left-hand side terms in the Y momentum equation you will see that they are actually in the order of delta over C, and they are indeed very small. So nothing will be left under the approximation of thin boundary layer, delta over C small. Only thing that will be remaining from the Y momentum equation is only one single term, dpy, dy, the Y derivative of the pressure being equal to 0, approximately, after dropping small terms. Small terms. So this is indeed the Y momentum equation for a thin boundary layer. Okay, that's the only thing that is left. Only the entire left-hand side becomes 0. The viscous terms are not 0, but negligible, I can say, a very small order of magnitude. The viscous terms, they are very small order of magnitude in the Y momentum equation. So this term is dp dy in the Y momentum equation. So we only end up with one term, dp dy is equal to 0 in the dimensional sense, or dp star over dy star is equal to 0, but it's the same thing because it's equal to 0 anyway. So therefore, what is left, this dp dy is equal to 0, is the is basically the Y momentum conservation equation for a thin boundary layer. Thin boundary layer, which means that when I say thin, delta over C much smaller than 1. So now we have three equations. Mass conservation, not changed. I mean, no simplification after because of the thin boundary layer. X momentum equation, more or less the same. We only lost one term when we applied the thin boundary layer concept. The Y momentum equation almost entirely disappeared. We only end up with dP dy is equal to 0 when we apply thin boundary layer concept. Now I will summarize all the equations and rewrite them, but this result is very interesting because I would like to talk a little bit about its implications. So if we have, for example, I mean, okay, let's generalize. Let's talk about an airfoil, even not a flat plate, but an airfoil. Let me delete this. So let's say we have an airfoil, so some kind of wing, and let's say we have an attached flow on top of it, so not separated, but we have a reasonably thin boundary layer growing on its surface. Okay. So that this thin boundary layer approximation and therefore the boundary layer equations that we just derived are applicable. If that is the case, this equation tells you, look, if this is your XY coordinate, if you are on the surface of the airfoil and if you move along Y direction, pressure will not change. dP dy is going to be equal to 0, so it's not changing with Y. It's constant along Y. This is interesting because why? This means that anything that I calculate, for example, I calculate pressure distribution from an inviscid theory, like panel method, okay? That panel method finds some kind of pressure distribution, and mostly we say that, okay, this is probably pressure distribution, you know, outside the boundary layer and everything, because we ignored the presence of the boundary layer. But the boundary layer theory says that it's fine. It doesn't change all the way to the surface. It is constant. So basically, the pressure distributions that we calculate, even from inviscid theory, using panel methods and everything, will be basically very close to the actual pressure distribution, if not identical. I mean, if the boundary layer is very small, thin boundary layer, the panel method pressure distribution will be your viscous pressure distribution. It's going to be the same because of this reason. And this is the main reason why we use extensively, for example, panel methods. Although they are inviscid and everything, we use extensively panel method-based tools when we are designing airfoils, when we are designing wings. And you have used, for example, X-foil, I think last semester, right? X-foil is a simple panel code. It does solve these boundary layer equations as well, if you want. But the result that you get, even with the just without the viscous solution, will be very close to that you get with the inviscid solution. There will be some minor differences though, due to some flow properties that we're going to discuss within a few weeks. For example, one flow property is that if we have this thin boundary layer, but for at high enough Reynolds numbers, the boundary layer actually goes through what we call a transition process. Generally, we will see those later, but the boundary layers start as what we call laminar boundary layers. They go through transition, and then suddenly the boundary layer thickness increases a lot to a turbulent boundary layer. If this is the case, inviscid solution will have to be modified slightly. And I'm still saying slightly. I mean, you do not have to have a major change. You get your panel method CP distribution, And because of this transition process, and because of the fact that the boundary is a bit thicker but still attached, the CP distribution gets modified a little bit. Okay, so therefore, this is the boundary layer theory also tells us that it's actually useful to know or apply the implicit flow theory like panel methods in aerodynamic analysis. Okay, just quickly let me recap where we are in terms of our equation sets under the let's say in the sense of thin boundary layers. We obtained, and I will write the dimensional form of the equations. We have the continuity equation d dx rho u plus d dy rho v equal to 0. Okay, and these are now what we can call boundary layer equations. We have the x momentum equation rho u du dx plus rho v du dy is equal to minus, I will write ordinary derivative now for pressure, and I will put a subscript e. What is the subscript? We will see later. dpe dx, and why I used ordinary derivative instead of partial derivative, I will explain. And d dy of mu du dy, partial derivative, and the y momentum equation as we have just discussed, dp dy is equal to 0. That's it. So there's no y dependence of pressure. Pressure is on x. That's why we had an ordinary derivative here. Okay. Boundary layer equations for, maybe I should say, 2D flows. Okay, so we are only interested in x and y momentum. And if I write the energy equation for the boundary layer, which we did not derive, but I will directly write it. The h dx is the enthalpy. So this is basically convection of enthalpy. And on the right-hand side, we have heat fluxes and pressure work, and also viscous work. And we have right now 4 equations, but we indeed have more than 4 unknowns. So we use also, as we did in the compressible flow case, we use the equation of state. So P equals rho RT. And we know that the enthalpy definition, enthalpy is indeed related to temperature, so Cp times temperature. So this equation set, let's zoom out, is our complete equation set for a 2-dimensional thin boundary layer, okay? Which includes which represents the physical principles of mass conservation, momentum conservation, and energy conservation. This equation set, of course, must be subjected to some boundary conditions at the wall, which we have already seen, but let's write them again. At the wall, which means that at y equal to 0, we have no slip boundary condition. So at the wall, we have basically u equal to 0, v equal to 0, and if there is some temperature boundary layer, t equal to t wall. Okay, and as y goes to infinity, so getting outside the boundary layer, u approaches to u edge and temperature approaches to t edge. So these are our boundary conditions that are necessary to solve this set of equations to actually find boundary layer properties on a solid body. The question is, how do we actually solve them? We will start seeing examples of this. The first solution, the concept of the boundary layer historically introduced by Ludwig Prandtl, and the first solution of the boundary layer equations was obtained by his student Blasius. So actually this was his thesis work when he was a graduate student, and his advisor was Ludwig Prandtl. So he obtained first time a solution for these boundary layer equations for a simple case, of course, for a simple flat plate case, two-dimensional flow, for incompressible flow, and for what we call a laminar flow. We will see those definitions later. So for the simplest case that you can get, he obtained an analytical solution, not a numerical solution, analytical solution to this set of boundary layer equations. Starting from next week, we will see what Blasius actually did in his thesis work, how he actually solved the equations. Okay, so let's stop here. Do you have any questions? Okay, then let's stop here and let's continue with the Blasius's solution that he attempted to do, and we will start learning it next week. Okay? Peki.